Human parity in automatic translation, is that even possible? I can tell you that machine translation has surpassed this human's ability to translate between Estonian and Korean a long, long time ago. But it turns out that surpassing or even meeting the quality of the professional human translator is quite a challenge and has really been the holy grail of machine translation research for the last 60 years or so. Until today, or maybe a couple of weeks ago, that's right. Today we have Hani Hassan Awadallah and Christian Federmann report on the project to achieve human parity. That's the parity with the kind of human who is a professional translator. Hani and Christian both work in the Microsoft Translator team. That's the team that builds the translation service that powers translations in Microsoft products and in many third-party products. Hani is a principal research scientist in the team, focused on advancing the foundational technologies that form the core of the translation engine, the piece that we call the decoder. His interests are in the areas of machine learning and deep learning applied to machine translation, natural language processing, speech translation, and semi-supervised machine learning. He completed his PhD at Dublin City University after finishing his master's at Cairo University. He started working at IBM in 1996, where he was also a member of the IBM team working on machine translation. He has been a member of the translator team since he joined Microsoft in 2010. He's responsible for the major breakthroughs that enabled us to ship speech translation in Skype in 2014, namely the technology we call true text, turning what a person said into what the person actually meant to say, and making machine translation friendlier to social media and colloquial utterances. Christian is a senior program manager in the translator team. He owns evaluation methodology, and he owns orchestrating the actual evaluations with human judges. He's the gatekeeper for quality for every release and every update the team makes to the production systems. He defined what human parity means for translation in concrete, provable terms, and was responsible for gathering the results in a meaningful and fully traceable way, because you can assume that making such a claim invites a lot of scrutiny from the other people working in the field. Christian finished his PhD in machine translation at Saarland University in Saarbrücken in 2013. He has been leading MT evaluation since that time, including defining and managing the evaluation for industry-wide MT competitions, namely the workshop on statistical machine translation and the international workshop on spoken language translation. Christian is also the author of the open source tool Appraise, which is used for running all of these evaluations. You can ask him after the talk how to make use of this tool and how to contribute. Now let's start. Found in translation, achieving human parity on Chinese and English news translation.
Thanks, Chris. So good morning, everyone. Thanks for being here today. Christian and myself will introduce you to our journey trying to achieve human parity on English, Chinese to English news translation. That was a wonderful collaboration between our Microsoft team at Redmond and MSRA teams, deep learning team, and NLC teams at China. So the paper on archive, and we have many outstanding researchers collaborated on that effort. So first, the internal project name or code name for that project was Project Babel. And you can imagine that Babel is correlated to achieving such high quality of translation. But we started at the beginning trying to answer two main questions. The first question is the machine translation quality is now high enough or approximation to the human parity, or how far we are. The second, which is more fundamental questions, how we can measure that. On other fields like speech recognition, for example, it is easier to measure the human parity. In translation, it is even much harder to measure the quality rather than the human evaluation. We will cover in that talk how we achieve the human parity and how we measured it. There was claims like around 2016 that the new wave of neural machine translation is approximating human parity. Now we can be sure about that we are really achieving that human parity. I like that sketchy timeline for machine translation from Chris Manning 2016. It is very sketchy, as you can imagine, because it is not actually based on some numbers on the MT quality side. But machine translation has been a dream for decades. Starting from the 40s and 60s, people start to look at machine translation as a problem that can be solved by computers. At around the 60s, people stopped looking at that due to some skepticism about how a computer can do reasoning. Still, as of today, we don't do any reasoning, but we are getting better in translation. So around the early 90s, there was a breakthrough in translation when statistical machine translation has been introduced based on information theory. And from that time, a lot of momentum for the translation has been gained, mainly introducing phrase-based translation in the mid of the last decade. And that enabled us and all other players on the online machine translation, Google and others, to shape online translation system that is really scalable and of good quality. Eventually, research community started to add syntax based to the translation, phrase-based translation, but still it is being noticeable that it is machine translation, not human translation. Till around 2016, when the new wave of neural machine translation started to be mainstream, and at that time, we start seeing good momentum for the neural machine translation. As of today, we can modify Chris Manning chart a little bit by adding our milestone of achieving human parity, and we still think there is a lot of remaining problems to be done and solved on machine translation to reach better quality. Okay, so we will have an overview of the current state of the art of neural machine translation. Then we will go through our contribution in that work. Sorry, I keep reading the transcription for debugging purposes, but it looks okay in general. Okay. Okay. So the main approach for neural machine translation is called encoder-decoder. In the older day, when we started doing phrase-based translation, we used to split or chunk the input sentence into pieces. These pieces we call the phrases, and for those phrases, we seek to translate each phrase on its own, and then eventually we use language models to put pieces together. And as you can imagine, this introduced a lot of disfluent output on translation, and that was the main characteristic of the phrase-based translation. Encoder-decoder framework for neural machine translation has been early proposed around 2014 by two different papers, and it mainly tries to achieve full representation for the input sentence and use that representation for decoding the output word by word. And in representing the encoder, a lot of approaches has been proposed there, but mainly the mainstream component follow the encoder-decoder architecture. As you can imagine, that is more, at least, appealing for the human cognition, because when you are trying to understand or translate a sentence, you really look at the full sentence, trying to understand the meaning and get the representation from there. The actual representation of the encoder at the first mainstream neural network, neural machine translation system was based on encoder-decoder framework. and it tries to represent the input as recurrent network. In recurrent network, you go through time step on each word, trying to learn the full representation for the sentence at once. And then by the end of the sentence, you have a state that you can use to generate the decoding step by step. That was very surprisingly for the whole machine translation community that it worked at the beginning. And yeah, it is very simple. It is just bilingual language model that use simple end-to-end model to produce translation. It works quite well for shorter sentence, but not for the longer one. For the longer sentence, I can imagine that you are not seeing the title of the slide at all due to the transcription. But yeah, it should be okay.
You can move it to the bottom. Then.
Okay, to remove something in the bottom. It's okay. So mainly, yeah. How you remove it from here?
You go to
The dot, dot, dot.
the dot bottom right. Yeah. Top right. Sorry.
Would people give the feedback, to show it at the top with interference? So maybe we should actually think of a different way.
We just need to say 3 very short things, then we can read.
Yes, okay. So the main breakthrough in neural machine translation was the introduction of the attention-based model. On attention-based model, unlike the sequence-to-sequence encoder-decoder model without attention, it can represent longer range representation. Instead of depending on the last state for representing the whole sentence, we have soft distribution on all possible states. Mainly, we can query the similarity between the current word we are trying to translate and all other words on the sequence of the encoder, and we end with soft weights that we can normalize, and we end with a soft distribution on all possible states. And that gives us flexible representation for the input sentence based on which word we are translating. And that is really what enabled neural machine translation to work across all different approaches. So the mainstream approach now for sequence modeling is RNN-based approaches. It is very efficient representation. Our products are based on that actually currently, and it can get a lot of help from the attention-based for long-range dependencies. Though it has a couple of limitations. Mainly, it is very hard to parallelize. Second, it has to go through sequential computation for each time step, and harder to catch long-term dependencies. Some other approaches start to appear to try to overcome such limitations, mainly convolutional-based approaches by FAIR and Google ByteNet and WaveNet. WaveNet is, again, encoder-decoder architecture that is now the main state-of-the-art for text-to-speech, for example. Moreover, newer approach starts to depend only on the attention, which is the attention all-you-need model transformer proposed by Google Brain team. And here we just relieve the whole constraints of sequential operation and move everything to the attention phase. Instead of having a recurrent network to model the encoder-decoder, we use what is called self-attention, in that each word can attend to the next words in the sequence. This nice visualization representation for the attention model, you can see the encoder are going step by step, calculating the attentions between all sequence on the source side. Then at decoding time, start calculating the attention between the source and the target, as well as different targets. and keep generating in that way. It uses only the last layer on the encoder, and it uses the left side of the decoder. As you can see here, it is very easy to parallelize all those operations because there is no sequence dependency. It can be just two matrices that multiply together and that can speed up the training process massively. So let us take a closer look on the transformer model because that was being a main component that we are using on the human parity project. So start from the encoder, we have input embeddings, and since the transformer model doesn't know anything about the position, we add positional encoding to that as well. And then we step by step try to have layers of that multi-head attention over all sequence of the inputs, along with residual and normalization, followed by feed-forward network. And this all represent one single layer that we have many of such layers there. At the decoder side, we follow exactly the same architecture, though here it is masked because we don't want to look at the right side, only the left side. Then we have multi-head attention between the source and the target, followed by a feed-forward network. And all this has, again, one layer only, and we have like 6 layers among those. Transformer model now represents the state of the art on neural machine translation, and we are using it in most of the systems that we are reporting today. So we will cover the areas that we explored during that project. You can imagine that we explored a lot of other areas, but at least we are here covering what works. A lot of that approaches we tried didn't work actually. So we are trying to explore 2 main directions here. First, how we can explore the duality of the machine translation problem. The duality of the machine translation problem means that we can have 2 different problems that really help each other. The first is translating from, for example, Chinese to English. The other is translating from English to Chinese. If we can get the systems to help each other to refine their translation, that is the duality of the translation problem. And we explore that duality in many components and areas in our system, as we'll show later. To give some contrast between duality and back translation, which is widely used on the research community, and we are still using back translation as well on our work. In back translation, you start with bilingual training data. You train a reverse system from English to Chinese, for example. Use monolingual data to generate synthetic training data, and combine that with the original bilingual data to train your system. In contrast to the duality of the MT dual learning approach, we have some limitation for the back translation. First, if you have bad translation, it will be propagating toward your system. You don't know how to judge if it is good or bad. In the dual problem, the other system can guide you if it is good or bad. The second, in back translation, you only depend on the target monolingual corpus, not source and target. In the dual learning, we can depend on both source and target. And for sure, for dual learning, we can use it both supervised and semi-supervised. In our work, we deploy and utilize both back translation and dual learning for improving our system. The first use of dual learning, we use it in unsupervised way. In that setup, we have monolingual corpus in both source and side. And in that, we can use a lot of feedback signals during the dual learning loop to learn how to improve the system. First, we can start from the English sentence here and move it to Chinese using the first system. Then we bring it back using Chinese-English translation. Then we have the original sentence and the round translated sentence. We can calculate the reconstruction cost and thus get feedback signal to the model how good is that whole process. The second, for sure, since we have monolingual corpus on both source and target side, we can use the language model to get feedback signals with how good those translations are. We keep doing that during our learning process to improve both models together. The second view for the dual learning is the dual supervised learning approach. In that task, we don't have monolingual corpus, but we still have two systems trained on bilingual corpus. And the main objective of that model is to try to minimize the gap and the differences between the joint probabilities of the sentence in the source and the target if it is produced in either X to Y or Y to X. And that is very helpful in refining the translation model as well. In the work of the Human Parity project, we deployed both supervised and unsupervised in the same way, in the same setup, I mean. And we do that online during training. Like for each mini batch, we pick one mini batch from that direction, another from the other direction, one mini batch from monolingual corpus X, another from monolingual corpus Y, and keep training and improving the models. Another approach for utilizing the duality of the machine translation model, instead of trying to do that on online fashion, like we did with the dual learning approach, we do that in batch mode. In other words, we train a baseline system using only B0 system here and there, using only the parallel data. And using that system, we can use the monolingual corpus on the source, monolingual corpus on the target, to generate pseudo-parallel data for the both systems. That comes with scores on how confident we are on that translation. We train a newer system in the first iteration for both directions, keep iterating 4 or 5 iterations over that to improve our system. As you can imagine, it's very similar to the dual learning, but that is not done in batch online mode. It is done in more expectation maximization fashion, when you try to train the whole systems and refine the probabilities at each iteration. There is some theoretical foundation for that from EM perspective, and the second is that you are propagating a lot of the gradient on very large batch mode rather than doing that on the online mode. Both approaches have been tried and both helped a lot on utilizing the duality of the machine translation problem. So far, we covered the dual learning and joint training. Second problem we focused on the bias for the left to right. During translation, we usually translate from left to right, and that causes a problem in that we are propagating the errors. At training time, we see the true examples. During decoding, we see the expected, predicted examples there. If we produced a problem or error at the beginning, it will be amplified quickly till the end, especially if the sentences are quite long. Again, we explore 2 different approaches to outcome such problem. The first is, what about if we do multi-pass decoding? Like, rather than decoding the sentence once, what about decoding it twice? And that is very coherent with what humans are doing, actually, because when you are trying to translate or understand a sentence, you can write it once, revise twice, revise 3rd time, and so on. How we do that, actually? We do that in 2-pass decoding. At the first, we run an encoder as usual, and then we run first-pass decoder, full system trained end-to-end to produce the first-pass decoder. From the first-pass decoder, we take the output of the first-pass decoder, augment it with the output of the encoder, and pass that to a second-pass decoder. The second-pass decoder now has full view of the source and a rough estimation of the full sentence in the target, and that can help a lot on getting the translation in better quality. In more concrete way here, that is formalization for the model of the problem. We start with the encoder. Whenever we finish the encoder, that is the last layer of the encoder, for example, transformer model, and then we start decoding the first path. Rather than predicting the actual word, we take the last layer of the decoder before softmax and feed that into another, through a gate to another decoder, as well as augmented or concatenating the encoder path to that second path decoder. If that is a transformer model, the second pass decoder now doesn't have to follow the constraint of looking to the left only, not the right, because here you have full view of the rough sentence from first pass, the full source sentence, so you can do full attention on both source and target to revise your translation. And that is proved very good approach to get better quality. Second approach, try that. That is done as the deliberation networks are done as two-pass approach when you have to do two decoder at the runtime. We can think of another way of doing that, simply trying to retrain the model in some way to respect that agreement between right to left path and left to right path. And again, we do that using okay. Yeah, I'm missing a slide here. Yeah. We do that simply similar to what we did with the joint training, but instead of doing joint training on source and target, we do it on right to left model and left to right model. In the left to right model is the usual model we train. The right to left model is the other model we try to predict English from the last word first, for example. If we can get the two models to agree together, then we seek better agreement between both right to left, left to right translation, and that can help in solving such problem. Now we turn our attention to increasing the amount of training data we have so far. Using the above approaches, we ended up with many different approaches, many different systems. Still, up to that point, we are using standard WMT training data along with monolingual data through the back translation, dual learning, and joint training. Ended up, we are ending around 35 million sentences. We thought that we may scale up our approach to more data, but with that comes more noisy data from the web crawl data, and we turned our focus on how to pick cleaner data to help our model. For that, we proposed a new approach as a multilingual sentence representation using multilingual system, and we end up with a sentence representation for each sentence in our parallel corpus, hundreds of millions of sentences, and then we measure the proximity or the similarity between the source sentence and the target sentence. Based on that similarity, we can decide if the two sentences are good translation to each other or not. Simply, we do that using sequence model again, but at that time, the model is trained as a multilingual system. In that case, it is bilingual only. The input can be either English or Chinese. The output can be either Chinese or English. The system doesn't know what is the input sentence, and it always can produce the correct output. That is multilingual system. It is slightly less quality than a dedicated one-directional system, but works quite well to get us a representation for a given sentence, regardless of the language. We end up with having the same exact representation for each sentence, regardless either Chinese or English. Okay, how we utilize such systems? We run the encoder part only of the joint system that we're training, the multilingual, giving English sentence or Chinese sentence. We end up with averaging over the context representation for each word and get the sentence vectors for calculating the cosine similarity between the two sentences. It proved to be a very good approach even in detecting bad translation, partial translation, or even machine translated data, because some of the machine translated data from very old systems are quite bad and quite harmful for the system. So we ended up filtering a lot of the data, but at the end, we can get cleaner data to fit our system more. We ended up with many systems now. As you can imagine, we tried the joint training, we tried dual learning, we tried two-pass decoding, R2L regularization, and we have many systems to try. And we opted just for trying system level re-ranking on the sentence level. And for that, we use features to rescore the candidates from the different systems and re-rank those candidates to pick the best system. We train such weights for system re-ranking on a held-out depth set, and we use many features that is listed over here. Among the features we are using, the original system score and which system produced which translation, regular language model, 5-gram model trained on the English news data, and we rescore both the input and the translation using another right-to-left system to see how good or bad the translation, giving the right-to-left constraints. We do the same with English to Chinese as well, like reverse direction. And we repeat that same feature rather than going through the system to score both translation. We use the sentence vector representation to measure how good or bad we are doing using that similarity score. So we now move to our experimental result. And we starting with comparing to 3 baselines. The first baseline is Goku baseline, which is the best system on WMT evaluation last year. And our baseline transformer model is getting us around 24 blue points. Adding the back translation, we get 25.5. And then we start trying our different approach proposed above, plus combination of them all. As you can see across the board, we are getting almost 1 and sometimes 2 blue points over the baseline plus back translation, which is quite large improvement. All those results are state-of-the-art compared to the last WMT evaluation, though it is not good enough to achieve human parity yet. Then that is the setup of the data selection with filtering more data, moving toward larger models. The base model, as I said, that is a transformer model with back translation. And when we have very large transformer model, when we use like 8,000 dimensions for the feed-forward network, we get a slightly better improvement with such large system. Then we start adding more data to see how far we can get, from adding 35 million more to 50 million and so on. And as we can see in the third part of the table, we can get a lot of improvement using the data selected, using the selection approach here. And we vary that with some dropout ratios because it can be very effective on training very large systems. So as you can imagine here, we ended up with many, many systems that we need to combine together. And as I said, the system combination is just a sentence level combination. So we start combining systems from different categories here. And we ended up with combining a lot of variations of the systems. And as the last combo systems here are the best performing, giving blue score on that test set. Okay, so far we have reviewed the approaches we have introduced. We have reviewed the neural machine translation. And before moving to Christian to review the human parity evaluation, that is among many of the research areas that's still worth investigating, that we didn't touch, and we think it will be of a huge impact in the near future. Low resource languages for sure, rare word problem and named entities, domain adaptation and topic adaptation. All our work here is sentence level. We don't get at all into the document level or context-level translation, like if you have a dialogue between two speakers, how to get the context into the game, how to get the document-level information into the game. Multimodality, text, speech, video, and a lot of signals coming from all those modalities can be used to improve the translation quality. We reviewed the different approaches, different architecture for neural MT. We still believe there is a lot of space for mixing and matching those approaches together in a specific transformer. CNN and RNN can play together in much efficient way to get better systems. And finally, returning back to the 60s, that we are not doing any reasoning, and we may want to still do some structure and understand what we are translating rather than depending on pattern-based translation as we are doing now. So now I'm moving to Christian, who will review the human evaluation.
Thank you, Henny. Test. Yes, that works. All right. We take questions at the end of the talk when we're done with the human eval stuff. So the basic premise of the whole human parity project was that now, given the NMT advances, we see MT quality, which is so much improved compared to the 60s or the 90s or the 2000s, that it seemed to be a good idea to now check if we can best Google's 2016 near parity by actually achieving proper human parity. What do you need to do that? First, you need to define what exactly you understand by human parity. So the obvious first thing is you do this in a direct equivalence-based fashion, where you basically say something when a bilingual human being assigns a quality, metric, score, whatever, to machine translation output and to human output, and this is equivalent in terms of quality, then at that point your machine has achieved human parity. That is a good first draft, but it's really hard to measure and determine what your equivalence of translation quality is. So that means instead of doing that, we inverse the whole thing and go for indirect difference-based approach, because that is something we can measure statistically by testing if there's a significant difference between the two systems. And if not, given enough sample points, we then can deduce that we have equivalence and hence parity. That somewhat flips the whole say, point of proof and burden of proof in our favor a little bit, because if we are simply unable of determining reliably existing differences between the two systems, the human and the machine translation system, then by our base assumption, we still have human parity. That's somewhat a point of criticism we ended up being flagged for, but at least this allows us, given a somewhat reliable scoring metric, to measure it and to provably claim we have parity based on the sample data points we collected. So yeah, and that's what I just said. So effectively, we jump from this equivalence-based direct approach, which allows us to imply or deduce human parity, to the not an absence of significant difference allows us to go for human parity. A nifty trick, worked out surprisingly well, as we will see in the following slides. An important thing to frame the whole discussion is our baseline assumptions, because the main feedback points we received after the parity announcement did not come necessarily from the research field, where everybody believes, okay, yes, you can do a sampling of data to form test sets, and then you can take segment scores and aggregate them into a joint metric of system quality for translation. But then you have end users, you have translators and people who believe that machines cannot really do proper translation. And for them, you have to state the fact that we have to assume this is possible, because otherwise the whole framework falls apart. And lastly, of course, without any sort of reliable metric of measuring quality, the house of cards falls apart and we cannot really measure this. Luckily, we have several such metrics, so we can proceed. Second, it was important, and we spent some care on the paper writing, making sure that we do not claim any superiority. So we're not yet talking about superhuman translation. We're barely touching the first steps of human parity for MT. So this is different from ASR, where you can measure your human level of quality and where some of the existing systems actually achieve superhuman performance. Second, it gives you no guarantees whatsoever that the translation output of a human parity system is necessarily error-free or always mostly right? Humans make translation errors, and our machine translation systems are not much different in that aspect. I guess we might even make more errors, but yeah, so it's not necessarily error-free. And lastly, given the fact that all of that is based on evaluation, on test sets and samples, of course, any of the results only correspond to the respective sample, so they need not generalize to the full set of potential scenarios, domains, problems. Though, of course, using random sampling, we hope that for a lot of those scenarios, our results would still apply. So that's the base of the whole thing. In terms of defining it, and that for the first time, so previously nobody ever dared talking about human parity because that immediately triggered knee-jerk reflexes from everybody outside your own research group telling you you are nuts and this is not possible. So now we tried to start off a very sort of hopefully agreeable definition on what human parity could be defined as, and then reformulating it in a way where we can measure it, so that now people can take our annotation output and check if that actually fulfills our definition, and then at some point they might concede, okay, you have parity for that sample or not. So that's the whole idea. I talked about the reliable scoring metric. So the question is, what can we do to measure the translation quality of our human translation system and our machine translation system? And one idea we have is everybody uses BLEU. So BLEU is stood the test of time and gets the respective award at NACL this year. Everybody uses that for tuning, for development, for evaluation. When I started working on MT eval, it was like 10 years back. It was more or less not so common that people ran human evals. So my main mission is to bring human eval to every MT experiment on this world. And everybody just reported BLEU. There was this short point in time where people diverged a bit, and the Meteor got some attention, TR, there's a nice set of metrics you could use. But at the end of the day, everybody goes back to using BLEU. It's nice and simple, and people tend to trust it. So, of course, given our definition of human parity, what we could do is we could simply use BLEU as our reliable scoring metric, take MT output, take human output, see how that compares against the BLEU test set, and then decide, okay, that's human parity or not. What would we need? We would need high-quality references, because otherwise, of course, the whole argument of human parity becomes somewhat weakened. We wanted to base the whole Chinese to English news translation parity project on what had been done at last year's WMT, because that's state of the art and sort of accepted in the research community. It was the right language pair. Sadly, what we did not have at the WMT 17 test set front was super reliable, high-quality references. So it was the first time we ever had Chinese in WMT inside the news share task, and some of the references were just not that great. So there's a subset of data which later was replaced with an improved reference, but sort of the trustworthiness of the WMT 17 reference translation was not that great. So we decided, okay, in order to make this whole thing fly, what we first need to do is we need to create additional references. So that meant we actually tried to measure two different things. One is we created a post-editing based reference based on crowdsourcing. That's a quick and dirty way of getting additional human quality or human level, human generated reference. But of course, it will not be the same level of quality compared to a full from scratch human translation, which is why we created the latter, the HT reference as well. So we could compare how does translation quality for a reference of a human from scratch differ to post-editing quality? And it's, of course, quite expected that they differ because post-editors will not be paid the same, and they will try to optimize their gain by being faster, so there should be differences. Now, having those two different human systems, we looked at how do things look when we actually compute the blur scores. So what you see here is, or what you can see because of the subtitles on top, there would be combo 6, which is that refers to the table Henny presented just before. So combo 6, combo 5, combo 4 would be our best combined systems from the Parity project. And then there's SOGO, which is the winning system from last year's WMT 17. And then there's 2 online systems, which happen to be part of WMT and also part of our evaluation campaigns throughout the Parity project. Now, this list of systems is ordered by decreasing quality according to all the human evaluation we did for the final paper. So that means combo 6, combo 5, combo 4 are better than SOGO, in this case significantly, and all 4 of them are better than the online systems. Now, the interesting thing is the only reference set for bleu which sort of captures that is the HT reference, because that gives us more or less the same scores for the combo systems, which makes sense. SOGO is a little worse, and then the online systems should be flipped according to bleu, but that sort of matches expectation. And then if you look at online B and the post-editing and the WMT references, something is severely odd, because based on those scores, we would assume maybe online B should be really, really, really great. And it consistently, in any of the campaigns we ran across the Parity project, so 15, a larger amount of campaigns since last year, the 2 online systems always ended in the last cluster. So they never ever jumped into a position where they would even somewhat become close to being second worst, right? So this was always really bad. And an interesting thing here is to see a system achieving 46, 48 blur points, but being completely and consistently penalized by human annotators. So at that point, we decided, a human blur score is not what we need for the Parity project. And instead, we really want to focus on asking bilingual speakers and not only ask them to compare output against references, because references, again, might introduce bias and or be faulty. So we actually opted for source-based human evaluation. So, quick summary of what that means for our measuring of human parity. So now we talked about definition and why blur is not the metric for that. So in order to proceed for parity, what we needed was this reliable scoring metric. In order to now that we already took the WMT test set from last year's WMT, we decided, okay, look at the human evaluation we performed there and adopt what they did, which is basically called a direct assessment. It's a technique where you take a pair of a candidate translation and some reference or translation hint, and you ask people to assign an absolute score between 0 and 100. You collect enough of those scores, and then over time you can identify spammers and random clickers, eliminate them from your pool of workers, and collecting enough data allows you later to determine system level quality for your set of systems. So that's adopting the state of the art from WMT 17. We then had our little requirement of going source-based, which is we adopted or changed the recipe to follow what we did last December for the IWSRT workshop, where we flipped from reference-based direct assessment to source-based direct assessment. The obvious caveat here is you now need bilingual annotators, which are harder to find and more expensive to pay for. In the context of our project, that was luckily not an issue. It is an issue for WMT and IWSRT because there, if your crowd pricing jumps from, I don't know, a couple of dollars per task to 10 times that, they will not end up getting enough data points, so the whole campaign is at risk. So, and last but not least, an important distinction to the previous campaigns and our human parity approach is that we wanted to make sure that really nobody could claim that our results are just random and we were just majorly lucky over time. So that means instead of just following the standard direct assessment approach, which is you take random sample of segments for system A, B, C, D, whatever, and collecting scores for all those segments, aggregating a system score based on those. We actually enforced that for every system we looked at, we compared the same segments. So the set of segments for all the systems is actually frozen and completely identical. That's the difference. In standard DA, it's just randomly sampled, so that over time, given enough segments, you will end up having a fair representation of system quality. And in our case, it actually is completely redundant, so that we can, for every segment, for all the systems, compare how they fared. And then to make it even more redundant, we not only had a single annotator per segment, but we enforced at least 3 of those. And as you see in a little while, or in the evaluation design for the final campaign for the parity thing, we tripled that again. So the final data we report results on is actually at least 9 annotators per segment per system for a lot of segments. So highly redundant, and we believe highly reliable. So that's why we put out all the data publicly, so people can use that to check and verify. For the final evaluation, an interesting twist on the evaluation campaign design is that campaigns or shared tasks like WMT and IWST operate on a once-a-year level, right? So they get a dump of systems and outputs, and they are only concerned finding this one ranking of systems in the matter of a couple of weeks, and then declare a winner, right? And then everything is forgotten about, and next year there's a completely different set of participants and a different campaign. In our scenario, we actually needed to have some level of continuity between the campaigns, because we wanted to inform system builders on our team how we fared compared to the other systems, so that we would measure progress over time. And that means we had to introduce some continuity between evals in the form of systems we always evaluated. That was also making the task harder, because we had to always carry 6 systems, which we kept stable across evaluation campaigns, which meant we basically wasted annotation mass for those systems, but at least it meant we could now fairly compare stuff over time. The rest is just small stuff. So we tested on a lot of different subsets. We ended up collecting roughly the same amount of data points than was collected for WMT 17. So it's a large-scale eval just for the purpose of our parity announcement. And we covered, due to the different subsets, nearly half of the 2,000 segments of WMT's news test 2017 test set, which is also a lot. So yes, this is the direct assessment base thing. The example just shows you the English reference-based thing from WMT last year. In our case, the reference would be the Chinese source text. And it's literally a very simple task. This is a lot faster, and it's a lot easier for people in terms of cognitive load when compared to the relative ranking tasks we did in the 2008 to 13 range for WMT. The nice bit is you can enforce reliability of scores by adding spiked data. So what we literally do is we have some source and a candidate translation, which gets scored whatever. And then what we do is we take the same candidate translation and we artificially destroy its contents by chopping off a phrase of a certain length relative to the target length. And then we know by swapping in something from a different system, which is completely unrelated on a different segment, that this cannot be same level of quality. So we know this is expected to be really worse in quality. And then if you collect enough of those and run significance testing, you end up having a good metric, which allows you to quickly eliminate random clickers and spammers. So, and as I mentioned, we have this enforced segment overlap. So again, reliable scores as much as we could make them. In terms of the eval campaigns, the rough timeline was that we conducted monthly large-scale evals for the current best research systems we had and our set of framing systems to make them continuous over time. And then the final round of evaluation campaigns happened in February, March this year when we approached Parity and found in one of our final evals, okay, we're there. And then we set up the big evaluation campaign described in the paper to be able to announce the whole thing. In terms of scale, it's literally WMT 17++ and a lot of redundancies, so it is as large scale as anybody has done it. So we can skip about that. Yes, let's just look over this. So this is just a quick look at the evolution over time. So the first eval from November was just the very first attempt at having a research system in the Babel Parity project. And we just compared that against the online systems and Sugo and our new references. And then over time, we had larger sets of systems and saw how the whole thing fared. Noteworthy is how online systems always end up being dead last, which confirms results from last year's WMT, where they also did not fare well in the human eval, so that's consistent. And then the interesting thing is how the research systems over time more and more closely approach quality of the human references. So what's missing here is the watershed moment in February, at the end of February, in a one-off eval, when we figured out that our combo systems actually jumped into the same result cluster. And that was the point in time when we decided, okay, now we need to set up the whole thing, see if we can measure the whole parity finding and prove it. And the tables you saw there actually are the result clusters from WMT lingo that is based on pairwise comparison of systems. It's not very intuitive and it's always confusing, so we have a much nicer representation coming up next. In a nutshell, what those tables mean is that each of the systems in a high cluster, so in the first rank 1 cluster, outperforms significantly all the systems in lower ranked clusters, right? And that means for some system if it is significantly better than some other systems, but then within the same cluster you have no idea if it's better or not, because in that same cluster you have this underlying assumption of if I cannot prove a significant difference, then it is equivalent by our definition number 2. And then you have the z-score and r-score that are just used for sort of to provide an ordering, because people like to see stuff in some ordered fashion, but it doesn't really tell you much. Specifically, the differences in deltas between the standardized scores, the z-scores, don't tell you anything. And the rest is just the average score the system achieved from this 0 to 100 scale, which tells you a bit, but also, I mean, it's hard to tell if the 0.5 between combo 6 and reference HT means something, or what they exactly denote or not. And then considering that reference post-editing is still in the same cluster but has significantly lower scores in R-score and Z-score, the whole thing is, it works as a means of properly computing result rankings, but it's hard to interpret for human beings. So what we do here is, for the rest, I just show you the final results for the parity claim for our best systems against the respective runner-up systems, and give you a graphical way of understanding the whole thing by moving from the result clusters, which contain just all the systems, to a pairwise density-based representation. And this now looks a lot more, a lot nicer, and is hopefully easier to interpret. What you have on the x-axis is just the scores ranging from 0 to 100. So that's literally the range of the slider the humans had to assign quality. And then you have an overlaid version of the histograms of the score bins, and then you have the corresponding density functions for the two systems. So what you see here is that the blue graph will always be our best combination system from the Parity project, and the gray one will always be a competing system. Here it's SOGO, so that's the winner from WMT 17. What you can see is the dashed lines are the mean scores for the two systems, and you see that for Combo 6 we have roughly 69 as a mean score, and SOGO is at 62. So there's an openly visible gap between the two systems, and you also see, based on the histogram and on the shape of the two density curves, that obviously the SOGO curve in gray has more area in the lower part of the whole graph, whereas the blue curve of the combo system it's at a lower level there, right? And this gives you sort of some understanding. If I now tell you that based on this, we claim that our system is better than the SOGO system, this is a much nicer way of framing it than this stupid cluster where you don't understand any numbers. Yes?
For the ones where both SOGO and us don't do that well, say
Yes.
60 or below or something like this, did we look at what's the correlation of the sentences? Are we bad with the same sentences, or are we bad for different things?
We didn't look, but you can, all the data is there. Or I can look, yes. No, this is, yeah, it's an open, as Henny said, there's an open research question for a lot of things, and that's one of the questions we will tackle. I mean, we use the same for our evals, so that is something I'm looking at a lot. But we didn't explicitly for this year. So now jumping back and forth between that SOGO, best WMT, and that's the WMT reference. So what you see here is, where is it? So here that's SOGO again, that's WMT. So the gray curve moves a little bit, but not much. The mean score is literally a little worse than for SOGO, but again, clearly this here backs why they end up in a lower cluster and we end up in a higher cluster. So again, more understandable how our system is better. Now it gets interesting. Now we jump to the cluster where post-editing and human translation and our system end up in the same cluster. That's the one where you see everything is indistinguishable. We don't really know how that looks like. And now it gets much more interesting. You see directly that the mean scores jump to being very close. And you also see that the shape of the curves somewhat converges in a sense, right? So, and here that explains in a graphical way what it means to be sort of indistinguishable. Right? And the main thing at the end is the jump to the human reference, where you literally have nearly perfectly overlapping curves. And I mean, except for some noise on the histograms, these systems seem to perform somewhat on the same level of quality. Now, an important point, Olivier brought this up, we don't necessarily know if the assigned scores for the respective bins sort of correlate to the same segments. So there might be some difference there, but considering that we collected tens of thousands of data points, bless you, the main take-home message here would be that to the best of our data collection abilities at this point in time, given the constraints of having the human evaluation people around, et cetera, these systems are equivalent, right? Or not significantly different, and hence in our indirect fashion they are equivalent, and that's why we end up having human parity in the end. So that was the final thing we then reported. This is a nicer graphical way of explaining those wonky tables. And following Henny's approach here, let's also talk about what we could be doing next. Of course, we released all the data publicly, which is not so common in the industry. So we encourage people to look at the data and tell us where we messed up so that we can improve on that. Improving the translation quality is something Henny had a ton of things NMT architecture work and modeling can do. Most importantly, people complained about us not being able to consider context in any way. We just have this sentence level approach. And an interesting comment or note was that it might be somewhat now possible to look at how does MT compare to humans of a certain certifiable level of translation ability for some scenario. I mean, we could build a test set or find annotators who have a certain certified ability, and then we can compare, is our MTs, I don't know, like first grade or fourth grade, I don't know. I mean, that's an approach or a direction we could look into. And it's noteworthy. So while this is parity, this is a statistical definition, we have enough data points to back that this actually is parity, not near parity, it's parity. It's only the first step on our trajectory towards having and reaching a fuller or more omnipresent human parity for MT. And there will be lots of new languages, domains, scenarios, architectures we can try and sort of try to push towards ever-increasing human parity-like quality. All right, and with that, we conclude, and I invite Henny up and we take questions you might have. Thank you.